So let me start from something that is non-trivial, but okay, now very much well established. That is the Mott transition, so how the Mott insulating state actually forms. We have the MFT description of this transition that corresponds to the formation of an insulating state out of an otherwise partially filled metal that, as effect of the repulsion among the electrons, leads to the formation of a gap at the Fermi level that separates two bands that are the Hubbard bands and that describe the excitations of holons and doublons with respect to the singly occupied states. We have a wonderful, as I say, a wonderful DMFT description of this transition in terms of progressive localization of the electrons, suppression of the quasi-particles, and the formation of a gap without symmetry breaking. That is an important point to stress. Why is this important? Well, because the Mott insulator and in general correlated states in this intermediate state are very important for quantum materials, as in the beginning for transition metal oxide like cuprates, but also vanadates and other kind of systems. More recently, also for twisted transition metal dechalcogenides or graphene. So a very large zoo of different compounds that host peculiar properties that are believed to be connected with the existence of a Mott state in the phase diagram. Now, recently, there have been some development both from theoretical proposals to actual measurements, not restricted only to correlated fermions, but also to bosons in cold atomic systems, but also from spectroscopical methods to measure the entanglement or the quantum entanglement in in this kind of many-body systems. There have been results that are connected to quantum tomography, partial quantum tomography of the system, or thermodynamic measurements, as well as direct measurements in the atomic systems of the parity or the occupation locally in a well-defined systems. This, of course, leads to a new view of what is the entanglement in this kind of system, what we can understand from the entanglement in the system, if we can get a better understanding of the Mott state, but also of the states that emerge from doping or other effect on the Mott insulator. So let me move on and give a little bit of warm-up about the entanglement. What is the entanglement? To understand in an intuitive way, let's consider two systems that we call state. The first one is a equiprobable situation where you have two parts of the system. Each part of the system can be realized with a square or a triangle, and you have all the possible combination of these two particular states. The other system is actually made only of combination that are either the same sign, so either two squares or two triangles. What we can understand from this is that if we measure what is in the part 2, so one part of the system, we can, in the first case, we have no information about what is in the first part, because the first part can be either in a square or in a triangle set. In the second case, instead, we deduce immediately from measuring 2 what is going on in part 1. This is, in all essence, in a very intuitive picture, what entanglement is. That is a lack of independence among different parts of the system, in this case, just 2. Okay, in a slightly more rigorous way, we can address what is interesting for us is a quantum state that we say it is entangled when this quantum state cannot be reduced to a product state, so cannot be written as the disjoint probability distribution of two states describing partition A and B. Of course, what is important in entanglement is the partition. So you can have different form of entanglement, this kind of description of entanglement, depending on what you, in the way you separate your system. You can have multiple type entanglement if you divide your system in multiple regions. You have bipartite entanglement, that is what we are mostly interested in. And of course, you can have a situation where the system is separable in the sense that if you create a partition, the two regions A and B that you create are actually independent one of the other. You can understand that, of course, this the state is actually the product of a square plus a triangle for part 1 and part 2. So this means it's separable and not entangled. Going to what is interesting for us, that is interacting fermions, we can consider, for instance, Half-Hilbert model. This is the simplest model we can consider on a lattice. In this model, we can assume, for simplicity, that we have SU2 spin symmetry and U1 charge symmetry. The existence of these local symmetries in the system guarantees that the density matrix, the local density matrix, can be factorized, okay, corresponding to the existence of conserved quantities. And this basically amounts to describe, to write down the density matrix, local density matrix rho I, in terms of parameters lambda for projector on all the four quantum states of the local Hilbert space. That is the empty, spin up, spin down, and W occupied side. These parameters lambda are actually dependent on the double occupation and, of course, the occupation of spin up and spin down. What we can understand from a very general point of view, this structure already tells us something that is corresponding to a partition of the spin space. So we separate spin up and spin down locally in our model. We observe that the reduced density matrix is actually describing a system that is in a separable state, as you see. And that means already that there is no entanglement among the spins. And I'm anticipating some of the results that we formalize later in a more rigorous way. This reduced density matrix also corresponds to something that is called pseudo-classical state, that has this form, and tell us that there are not quantum correlation among the spin, but only classical correlations. That is already something interesting to understand. So we move on to solve our model. Of course, solving the upper model is complicated. We know the MFT, so we can try to address what is interesting for us, so the Mott transition, using local dynamical mean field theory, the single site one. Of course, we create a partition that isolates the tagged site and impurity with the rest of the system that we know is described by above. We focus on two different quantities. The first one is the entanglement entropy, or entropy of entanglement, that basically describe how much our system is far or is different from a well-defined quantum state, very much like entropy in the Boltzmann entropy in a classical system. And we can also evaluate what is called the mutual information. The mutual information that is derived by the entanglement entropy, this is the local mutual information among the spin partitions, is basically describing how much of subset A, that is in this case spin up, we can obtain by measuring spin down. Or if you want to say it in another way, the common information, the shared information between the two partitions, as this Venn diagram expresses. What is interesting of the mutual information is that it provides us with a bound from above to all the correlations between the two parts. So in this case, between spin up and spin down. What is different from a local point of view? What matters the most is the fact that you can do mean field theory, and dynamical mean field theory enables us to take into account quantum fluctuations, local quantum fluctuations, that provides us with finite value of the variance of different observables and give the entanglement entropy a non-trivial behavior from the non-interacting limit of 2 in bit units to the Mott state that converges towards 1, and that corresponds to the formation of local singlets. The critical behavior has been analyzed in an old paper by Su et al. In 2013. And what is important here is also to stress that we obtain finite behavior of the local modal information among the spins that would be vanishing in the midfield approach. And this is telling us that we have the classical correlation, because as I say, this is a bound, that emerges from quantum embedding. So the fact that we can do dynamical midfield theory and we embed the single site into a BAT that's self-consistently constructed is a quantum embedding and give us the possibility of describing classical correlation. It is a powerful understanding of what the MFT does. Moving on, of course, we want to go beyond this local picture, considering cluster dynamical midfield theory. And so cluster dynamical midfield theory corresponds to embed a cluster in a self-consistent BAT. And this gives us the possibility of the understanding of investigating the behavior at short range in this cluster, impurity cluster. We solve this model by using 2 different approaches. One is exactly diagonalization, and the other is a adaptive sampling configuration interaction developed by Carlos Meguto Zahera, that is also a collaborator of us. This, of course, has a limitation in the dimensionality of the cluster we can analyze, but we gain the fact that we can work at 0 temperature, so we exclude any thermodynamic hassle connected with the construction of thermodynamic entropy, and these 2 methods give us direct access to the cluster reduced density matrix using a fast algorithm that allows to trace out all the BAT degrees of freedom that in a large system can be very time consuming from a computational point of view. With cluster DMFT, we can describe the Mott transition. Here is the evolution of the quasi-particle residue Z as a function of the interaction compared to the single site. We see that we have a transition between U in unit of the half bandwidth between 1 and 2. So what do we get out of this understanding, this investigation? First, we analyze the local and the 2-site nearest neighbor entanglement entropy, and we observe that these functions first are decreasing, very much like in the single site description. They show a large discontinuity at the Mott transition because it's of first order, and we observe a very weak dependence on the cluster size. It is important to assess the quality of the results I'm going to discuss later on, comparing exact diagonalization results for a cluster of 2 sites versus a cluster of 2 by 2, and larger cluster analyzed with configuration interaction. We see that there is a almost perfect agreement in the single site and a little bit more less good one for the nearest neighbor one. What is important to understand is, for instance, the evolution, the reduction of the nearest neighbor entanglement entropy in the non-interacting limit does not go back to the expected value of 4. That will be the value you get in the non-interacting limit. And it is due to the fact that in a cluster dynamical midfield theory picture, you have residual spatial correlation in the non-interacting limit that reduces the entanglement entropy in the non-interacting limit. Should this number correspond to 4, we would have mutual information among nearest neighbor to be 0. And in fact, we observe it is not. The mutual information is finite and decreases with increasing the correlation as it undergoes a very big jump in the Mott transition and decreases again. Importantly, the tail behavior of the mutual information is again the information shared between the two sites nearest site in the cluster decay with the same shape, the same tail as the local entropy. This is something that you can understand by looking at the average cluster average mutual information that is reported here. You take a single site I and you sum all the other sites of the system, L-1, and you can show by using entropy subadditivity, is a property of the entanglement entropy, that this quantity is bounded from above by the local spin entropy. So the two will decay with the same behavior, and they are, of course, shifted by a quantity, a finite constant. And armed with all this understanding, we obtain our first important result. That is the following. We consider the mutual information between two sites, not necessarily the nearest neighbor, in a large enough cluster. And as I said, this quantity bounds from above all the correlations that you can construct between the two sites in this case. This implies that the quantum correlation, that the decay of this quantity bounds from above also the decay of quantum correlation. So we observe by plotting the evolution of the mutual information as a function of the correlation U for different distances between I and J. We observe that for the larger contribution is obtained for the quasi-local correlation, that is for nearest neighbor sites. If we consider sites that are more distant apart on the diagonal or more than this, the diagonal, we observe a reduction of this quantity, saying that the quasi-local correlation are actually, in our approximation scheme, the most important one, the most important type of correlation. So is this the end of the story? No, but to get more insight into what the entanglement does into a correlated system, we have to go a little bit deeper in quantum information theory, and we consider what is called quantum information geometry. It is a geometrical description of the quantum information. To do so, we consider the set of all the states you describe in terms of density matrix rho. In this set, as normal, we want to introduce a distance that can tell us how far apart are two different states. One of these distances, it's actually pseudo distance, is the quantum relative entropy. It is defined in this way, that basically describe the distance between a state rho of interest with any other state rho prime in this set of all states. Note that this set is convex, so any linear combination of states is again inside this state. Armed with this distance, we can define other kind of subset of this set of all states. The first one is the trivial one, is the uncorrelated set of states. There are all the states that are here in this set of Riemann matrices that can be expressed as a product in two different partitions, and that exists, it corresponds to all the states that have a covariance between any two observables equal 0. So this quantity here is identically 0. Next, we can define the set of separable states. The separable states are basically a classic mixing of a convex combination of probabilities, sum to 1 of uncorrelated states. And this defines a convex hull of the uncorrelated states. So define this pinkish subset here. Inside this subset, we can define another set, that is the set of the pseudo-classical states, that again is defined as a classical mixture of states that can be described in each of the two parts in the orthonormal basis of some operators. So this one is the orthonormal basis for subset A and partition A and partition B. What we do with this set using the pseudo distance I introduced is to define suitable quantities. The first one is the total correlation. It is defined as the minimum distance between our state rho and any state pi of uncorrelated type, as this quantity here. Another quantity of interest is the relative entropy of entanglement. That is basically the distance, the minimum of the distance between our state rho and the separable states, so this quantity here. And the last is the quantum discord, that is the distance between our state and the closest pseudo-classical state. This basically describes the measure the quantum correlations of the system. You can divide that all the correlations are bounded, are basically the combination of quantum correlation and classical correlation that we know. What is important is that this quantity, the total correlation, we can actually evaluate, and you can construct and show that this quantity corresponds to the mutual information. Unfortunately, the other two, the relative entropy of entanglement and the quantum discord, are not easy to calculate, basically because evaluating this optimization is very hard. It's actually MP hard, so it's essentially impossible. Still, the hierarchy between this set here, that is the uncorrelated, is contained in the pseudo-classical, that is contained in the separable, gives us an upper bound to the quantity of interest, that is the relative entropy of entanglement. There is an upper bound, so the mutual information that again express the contribution to all the correlation, quantum and classical, in our state, bounds from above the entanglement. That is useful information, but we would like to have something more. We would like to have something that bounds from below our quantity of interest. That is the entanglement. As usually in physics, when you are in a dead end, you can invoke some help from symmetry. As I was sketching at the beginning, the existence of local conserved quantities in our system that can be charge, parity, magnetization, give rise to a factorization of the rotation matrix and thus of the reduced density matrix. That then assume this form where you have a number of non-zero elements among all the states connected by the as allowed, enabled by the existence of the symmetries, and you would like to understand what is done here. So now, to analyze better the situation, you have to consider two different inputs. The first one is the PPT criterion, that is the positive partial transpose criterion. This basically establishes a method to construct a separable state. So given a density matrix rho, it tells you, given a bipartition A and B, tells you if this state is a separable state or not. Of course, it is a sufficient condition, but it's a necessary condition, but becomes sufficient also for a small enough system, 2 by 2 or 3 by 2. That is our case when we take into account the symmetries. Of course, otherwise the system is very large because it corresponds to the cluster. This result was put forward by Perez in this work in 1996, and the Horodecki family, I would say, because it's the father with the two brothers, Horodecki, that contributed in this. And it's reviewed by this physical review paper here. It's very interesting. The second ingredient that we need is the super selection rule. So we have to stop 1 second and ask ourselves, how can we extract entanglement in a physical system? To extract entanglement, you have to act locally with some operation, and you would like this operation to preserve the charge or the parity of your system, very much giving you an extension of the conventional selection rules that you have in quantum physics. These super selection rules can be, in our case, we consider the number and parity conservation, and basically put a constraint on the element of the reduced density matrix of our system that can actually be non-zero. So it sets to zero this grayish, dark and light gray elements, depending if you consider charge or also parity super selection rule. And of course, this simplifies the form of the rho and gives us the possibility to actually implement the PPT criterion to check for a separable, the closest separable state. In this way, we can construct, and this was also put forward by Lexing Ding and Christian Schilling in a number of papers and it's very well explained in the Lexing-Ding PhD thesis published on the archive 2 years ago. And it gives us the possibility to construct a lower bound to the entanglement in terms of a quantity that we can actually calculate from the knowledge of the density matrix. If we implement these ideas in our cluster DMFT calculations, we obtain this plot that is basically bounding from above and from below the entanglement, the impurity entanglement of a finite system, of finite quantum system. And there are several observations to do. First, that we can identify the region, even though we cannot identify the entanglement curve, we can understand, we can isolate an entanglement region, a finite entanglement region in our system as a function of the correlation. We observe three important features. The first one is that the entanglement of the Mott phase is actually larger than the entanglement of the metallic phase, given the lower bound. And this is important because, if you recall, the description of the entanglement entropy, local and non-local, was decreasing function. Was suggesting that somehow the Mott phase was somehow less entangled than the metal. The second clear point is that the lower bound, so the super selection filtered entanglement, is actually giving a very sharp signature of the metal-insulator transition. That's something that can be, in principle, you can imagine to be measured in atomic cold atoms setup. And the third is that the charge super selection rules can cancel almost completely the entanglement in the metallic region that is due to variation of the local charge, so due to the transport, the localization of the electrons. As well, we can apply these lower bounds, so the super selection filters, to the mutual information, the nearest neighbor mutual information, and we can basically disentangle the contributions to the nearest neighbor unrestricted mutual information. And we observe that whereas the unrestricted was actually decreasing in the metallic phase here, we observe that the restricted one, the super selected filtered mutual information, is actually increasing, undergoes a sharp discontinuity, and almost gets flattened in the Mott phase. Very much so. This decay cannot be contained in the charge or parity part of the reduced density matrix. What you can get further from this analysis is the entanglement negativity. Again, using the partial positive transpose criterion, you can construct a quantity, the negativity, the logarithmic negativity, that you can use to, these are the lambdas, are the eigenvalues of the transposed density matrix, in this case, the quasi-local density matrix. Constructing this quantity, you can get a upper bound to the distillable entanglement. That is another measure of the entanglement in terms of distillation in pure Bell state. So it tells us how much the state we are looking at can be reduced in some sense into a set copies of pure Bell states. Why this is interesting? Well, because other than giving us an upper bound, we don't have a lower bound here, but looking at the spectrum of the density matrix rho ij for the Mott insulator, you can clearly see that the largest part of the contribution to the spectrum comes from a singlet state, and this is suggesting that the entanglement in the Mott region, in the Mott state, is of distillable kind, so can be distilled in terms of pure Bell states that you can actually use to construct entanglement. So we can do something more, yes, other than understanding what is in the properties of the Mott insulating state. we can actually get interested in states that are close neighboring to the Mott state, as I was discussing at the beginning. The most famous or the most important of which is the pseudo-gap region that you can construct by hole doping the Mott state. Here we investigate the formation of these pseudo-gap states by considering hole doping of the Hubbard model using a 2x2 plaquette in cluster dynamical mean field theory. We can construct a phase diagram in terms of the interaction U and the chemical potential mu, and you see that there is a region of Mott-Hubbard Mott insulator, and at small value of the doping and large values, at zero value of the doping and large value of the correlation, that becomes a Fermi liquid when you increase the doping a lot. Separating these two regions, there is a pseudo-gap metal phase that is actually separated, that is continuously collected in terms of doping and chemical potential with the Mott insulated state, but is first order separated from the Fermi liquid metal, at least in our 2x2 plaquette approximation. This was put forward in a work of Giovanni Sordi and Christian Aulet Tremblay 15 years ago. I know this is very debated description of the pseudo-gap, but so far we are sticking to this as a modeling of the pseudo-gap phase. Here is the evolution of the local density as a function of the chemical potential, and you see that it's a large discontinuity, and this pseudo-gap phase, this transition between metal and metal, and this transition, this phase that is continuously connected with the Mott-Hubbard. So repeating the analysis in this whole doped Mott insulator, we obtain a number of results that are preliminary. Sometimes we are still to be finalizing the publication. The first part corresponds to what the local site is doing in our embedding, and we observe, for instance, that the entanglement entropy by reducing the doping undergoes a sudden decrease before entering in the Mott insulator, whereas in the largely doped Fermi liquid, this is almost constant and decreasing on the other side. Note that the spin resolve entanglement is very large, very close to logarithm of 2, that is the Mott insulating value, but is slightly smaller. And what is important is that the local mutual information, so that describes again the classical correlation between the two spins in this mildly doped pseudo-gap phase, is increasing with a superlinear behavior before reaching the Mott insulator. The same superlinear behavior is observed by considering the nearest neighbor mutual information, and you see that there is a large increasing of the total correlations in our system before connecting the Fermi liquid to the Mott phase. What is important is this result here, is the behavior of the lower bound to the entanglement in the super selection filtered quantities. And we see that whereas the Fermi liquid metal has a zero restricted entanglement that is reported here, the pseudo-gap does not, as an increasing, again, also superlinear here, behavior that connects to the Mott insulator. This is suggesting that the pseudo-gap is a metal with very large correlations, but also with an entanglement that is in some sense more Mott-like, that is finite, whereas the Fermi liquid one is not. Okay, there is a way to frame, to describe in a more quantum information, from a quantum information point of view, what the pseudo-gap is. So I would like to conclude, my time is over. I first would like to acknowledge the people that worked in this results with Massimo in Trieste, and the main player of this work is Gabriele Bellomia, that I think is in the audience, a former PhD of us that is now looking for a postdoc, and that basically did all the calculation and the figures that you have seen in this presentation have been put forward by him in collaboration with Carlos Mejuto Zaera, that is also a very brilliant postdoc in our group in Trieste, that is now moving to LPT in Toulouse. I also have to acknowledge very useful discussion with several people, most important of which is Lexin Ding and Christian Schilling in Munich. I have finished. Thanks a lot.
Thank you very much for this great talk, Adriano. It's very nice. I already see Karsten's hand raised, so Karsten, go on.
Very nice talk, Adriano. I have two questions on the super selection rule. I don't fully understand it, I have to admit. So you throw away some density matrix elements and therefore you get less entanglement in the lower bound. A, is there more to that than this thing? And B, why do you do it? Because in principle with ED or CI, you can calculate all density matrix elements.
Yes, we do, but the point is that you need to restrict the values of the elements of the reduced density matrix to be able to implement the PPT criterion here. So the point is in what way you can measure the entanglement in your system. Okay, in the density matrix that you have here, you have sectors that correspond to the quantities that you see cannot be used to measure the entanglement because they connect states that have different configurations, local configurations in the single site. Because
so if you calculate the entanglement negativity, they wouldn't contribute.
This is a good question. No, I don't know.
Okay.
I guess they don't. The point is that if you look at the experiments here, okay, this is not very clear, but the experiments that have been done here are basically creating a cold atomic setup, a chain, two chains. This is for bosons, but it's not important. What they can measure is they can do a local measure of the parity, so they can count how many electrons with given spin is in each site of the chain. In this way, you can reconstruct the density matrix. We are going back engineering and doing the opposite, is that we are connecting a state that in two different sites have a different configuration. This is not going to, oops, what is going on? Is not going to contribute, very funny, it's not going to contribute to the entanglement measure that you can do experimentally. So you have to filter.
Yeah, okay, for that it might matter, okay. And if I may just to add something, so comparing to a Heisenberg model, what is your entanglement of this? So there you can do much larger cluster sites. It's also much better investigated, and for large you connect to it.
Yes.
Do you get at large U the same entanglement, or is this 2 by 2 cluster still way too small?
I don't know, because we didn't solve any Heisenberg-like model, but of course this model in the Mott, in the strong correlation limit goes to the Heisenberg model. So I expect the two to, as far as short correlation, short range entanglement is concerned, I think the two should match. Of course, should they not match, then this is, of course, querying the validity of cluster DMFT as approximation for this description problem.
Thank you, Karsten and Adriano. Dieter is next.
Yes, thank you very much. I really enjoyed these results on nearest neighbor entanglement. And thanks. In fact, you may even employ this to study materials. I'm saying that because Krzysztof Bitschuk, Walter Hofstetter, Jan Kunisch, and I in 2012 in a PRL used single-site DMFT and numerical renormalization group to compute the von Neumann entropy and relative entropy, and showed that this can even be useful for some transition metal oxides. Now you go beyond that because you calculate also nearest neighbor entanglement, and this may be very interesting.
Thanks. Actually, the motivation at the beginning was mostly as an experiment to understand the emergence of topological order in a very naive and unclear way to me. But yes, the point is, I mean, the motivation is exactly that. It's understanding what is the true, genuine nature of the Mott insulator beyond the correlation picture. That, of course, it's powerful and valid, but I would like to, you know, dig a little bit more, if possible. Of course, materials is the next step. Though to cast the MFT, probably it's a little bit hard. We need some more valid method, numerical method.
Yes.
Adriano, I see Andy next.
Hi, right. Thank you. Beautiful talk. If I understood correctly, what you were showing is entanglement amongst the states of the impurity model.
Yeah.
What can be said? Is it interesting to look at entanglement between the impurity model and the bath?
Yeah. That is a very, very good question that we actually addressed in the beginning of this journey. And it's a little bit more complicated because, of course, it depends very much on the nature of the impurity, on the impurity cluster, of course, you know, because you can have a pure state or not, depending if you have a formation of a singlet or not. It's not that I don't want to answer your question. The one is that we are actually working in exploiting entanglement as a way. This is an idea of Massimo. Is in exploiting the entanglement between the impurity cluster of single site and the bath to improve the dynamical mean field theory description of the construction of the bath, if you want. That's an important piece of information that also we are, let's say, working in two different parallel research lines. The other is using the density matrix renormalization group.
Right. Thank you.
Yeah, I'm sorry I didn't probably answer completely your question, but because I don't want to expose myself too much in this, but it's a very, very important question, actually.
Nice. Are there any further questions? So maybe let me ask one. So there have also been efforts by, as you also briefly mentioned, by Giovanni Sordi and André-Marie Tremblay. I think they calculated finite temperature properties, right, in the pseudo gap. Did you try to connect these two results? So let's say at t equals to 0 from your calculation and finite t from theirs.
Yes, our results basically, okay, what Giovanni did with Tremblay was basically to evaluate the local, using cluster dynamic mean field theory, you can evaluate the local entanglement entropy. Now, the local entanglement entropy depends on the reduced density matrix that in turn depends on the W occupation. You know the W occupation are different if you do single site or cluster DMFT. You have the indirect effect of the short-range correlations. Yes, we matched our results with theirs at different temperature. Of course, their calculations are a little bit different in the sense that they are trying to match the results of this paper here. It's basically this plot here. That is the contribution of both entanglement entropy and thermodynamic entropy in a Hubbard model that's been actually realized and measured in atomic systems. So yeah, they are very close, but a little bit different. Local entanglement entropy is not local in the sense you may think of. It's local in the sense that behold a single site, but contains all range entanglement with all the sites of the system, near and far. So it's a little bit a different beast that you want to handle. Mm-hmm. But to answer your question, yes, our results compare well with those of Giovanni.
Very nice. And maybe if I may ask one more question. So there is growing evidence, let's say, that within the pseudogap regime, you also get the tendency towards, let's say, a charge ordering or a charge inhomogeneity, whatever you will call it. Do you see anything like this in your calculations at t equals to 0?
No, because we constrain the system to be non-long range order, let's say.
Okay. But
You can implement long any kind
Right,
of Lagrangian on top of this, of course, but that would be then you have to do different types, yes. But it's an interesting direction to pursue.
Absolutely.
You want to compare two experiments, yes. It's a good point.